Welcome everyone to this explainer. Today, we're going to dive into the absolutely fascinating architecture of consistent hashing. If you've ever wondered how the massive systems we rely on every single day actually manage to power horizontal scaling without completely falling apart, well, you're in exactly the right place. Think about it for a second. How do the tech giants handle millions of concurrent users? When a massive surge of traffic hits a database, how do they keep the system online and lightning fast? There's a hard limit to how beefy you can make one single server, right? Eventually, you hit the limits of vertical scaling. So you have to scale horizontally by adding more servers. But here's the catch. Distributing all that data evenly across a constantly shifting pool of servers is an incredibly complex puzzle. So here's our roadmap for today. We're going to start with the rehashing problem. Build a hash ring to fix it. Tackle the tricky hotspot key problem, add virtual nodes, and finally, look at consistent hashing in the wild. Okay, let's jump right into section 1, the rehashing problem. To really appreciate the solution, we first need to understand exactly why traditional methods just break down under pressure. So a very common traditional way to balance load across multiple cache servers is using a standard modular hash function. The formula is actually pretty simple. The server index equals the hash of the key, modulo the number of servers in the pool. Let's imagine a fixed pool of 4 servers, labeled 0 through 3. We run our keys through a hash function, apply modulo 4, and the keys map out nicely and evenly across those servers. And you know what? This approach works perfectly, as long as the size of your server pool is fixed and never ever changes. But here is the villain of our story. What happens if a server crashes? Or what if we need to quickly add a new server to handle a massive traffic spike? Let's say server 1 goes offline. Boom. Now our server pool size is 3. The hash value for the keys hasn't changed at all, but because we're now applying modulo 3 instead of modulo 4, the underlying math is completely wrecked. Nearly all the keys are suddenly redistributed. It's not just the keys from that dead server 1 that need a new home. Almost every single key now maps to a completely different server. Your cache clients will start trying to fetch data from the wrong places, causing a catastrophic storm of cache misses that will literally bring your entire system to its knees. Which brings us to section 2. Building the hash ring. We need a geometric hero to save us from all this rehashing chaos. Enter consistent hashing. The foundational definition out there states that consistent hashing is a special kind of hashing where, when a hash table is resized, only k divided by n keys need to be remapped on average. In that equation, k is the number of keys and n is the number of slots. Now compare that to the traditional method we just talked about, where a change in slots caused nearly all your keys to remap. This algorithm dramatically minimizes data movement. It's a total game changer. To visualize how this works, let's assume we're using the SHA-1 cryptographic hash function. SH1 has a massive output range. It goes from 0 all the way to 2 to the power of 160 minus 1. Imagine mapping all those possible hash values out onto a giant straight line. Now take both ends of that line and physically connect them to form a continuous circle. Just like that, we've created our hash ring. With our ring established, the beautifully simple logic of the algorithm basically comes down to 3 steps. First, we take our servers using their IP addresses or names and hash them using a uniformly distributed hash function to place them onto specific points on the ring. Second, we take our data keys and hash them onto that exact same ring. Finally, to figure out which server stores a particular key, we just start at the key's position on the ring and walk clockwise. The absolute crucial point here lies in that spatial relationship. We start at a key, let's say key 0, and walk clockwise around the perimeter of the circle until we bump into the very first server. That's where the data lives. And because of this clockwise walk, if we remove or add a server, we only disrupt the hash space immediately adjacent to it. A crash server simply means its keys just have to walk a little bit further clockwise down the road to the next available server. The rest of the ring, and the vast majority of your data, is completely untouched. Boom, we've solved the massive cache miss problem. But before we take a victory lap, let's move to section 3, the hotspot key problem. As elegant as the basic hash ring is, it does have a couple of fatal flaws when deployed in the real world. The first major issue is keeping the partitions balanced. A partition is just a hash space between adjacent servers on the ring. If server 1 goes down and is removed from the ring, server 2 suddenly inherits all of server 1's partition. Overnight, server 2's partition is twice as large as the others. The distribution of our space becomes drastically unequal.
The second issue is non-uniform key distribution. Even if all your servers are perfectly healthy, the randomness of the hash function might accidentally place them very close together on one side of the ring. If your keys happen to land heavily in one massive, wide-open area, a single server might end up storing almost all the data. Meanwhile, your other servers are sitting entirely empty, doing absolutely nothing. And that brings us to what's known as the hotspot key problem, often called the celebrity problem. Imagine you're running a huge social application. Due to the random nature of the hash function, the data for Katy Perry, Justin Bieber, and Lady Gaga all somehow happen to map onto the exact same server shard. Suddenly, millions of fans are requesting that data simultaneously. That single server will be completely overwhelmed with read operations and crash under the massive load, while your other servers are basically twiddling their thumbs.
So how on earth do we fix this? Welcome to Section 4, Adding Virtual Nodes. This is the elegant engineering power-up that completely resolves these critical flaws. Here's the trick. Instead of mapping one physical server to one single point on the ring, we use virtual nodes, which are sometimes called replicas. Each real, physical server is represented by multiple virtual nodes scattered all around the hash ring. So instead of being just one dot, Server 0 is now represented by Server 0_0, Server 0_1, and Server 0_2. We've artificially multiplied our distribution points. When you compare the two approaches, the difference is night and day. Without virtual nodes, you get chaotic, wildly uneven partitions when a physical server goes down. But by using virtual nodes, the partitions are chopped up into many smaller, overlapping segments. If a physical server dies, all of its virtual nodes vanish across the ring, and its load is distributed evenly in tiny little chunks to many different physical servers, rather than dumping the whole burden onto just one unlucky neighbor. So you might be wondering, how does this change our routing logic? Well, finding a key remains exactly the same. We take our key, hash it onto the ring, and start walking clockwise. But now, the first thing we bump into is a virtual node. If we hit virtual nodes server 1.1, the system simply routes us back to the real physical server 1. It's the exact same spatial logic, just with a much more granular safety net. Now, as engineers, we know everything is a trade-off. As you increase the number of virtual nodes, the distribution of keys becomes significantly more balanced. In fact, research shows that with 1 to 200 virtual nodes, the standard deviation, which measures how spread out the data is, drops to between 5 and 10% of the mean. That is incredible balance. However, the trade-off is that you now need more space to store the mapping data for all those virtual nodes. You basically have to tune the number of virtual nodes to fit your specific system requirements. All right, let's bring this all home with Section 5, Consistent Hashing in the Wild. Let's ground all this theory into the real world. To summarize the core value proposition, engineers rely on this algorithm because it minimizes key redistribution when servers are added or removed. It enables seamless, automatic horizontal scaling. It accommodates heterogeneous server environments, meaning, hey, if you buy a powerful new server, you can just assign it way more virtual nodes than an older, weaker server. And crucially, it mitigates that hotspot celebrity problem by ensuring data is finely and evenly distributed. If you think this sounds like just a fun academic exercise, take a look at the heavy hitters that rely on it every day. Consistent hashing is the partitioning component behind Amazon's Dynamo database. It handles cluster partitioning for Apache Cassandra, it literally scales the Discord chat application, it drives the Akamai content delivery network, and it acts as the backbone for maglev network load balancers. Understanding this algorithm means you understand the very fabric of how the modern internet scales to serve billions of people. Which leaves us with a final question for you. How could you apply consistent hashing to horizontally scale your own next big project? Because when you truly understand the tools of the tech giants, the ceiling of what you can build gets a whole lot higher. Thanks for joining me on this explainer, and keep building.